Yeah. Okay, we're very happy to welcome Professor David Holgate today to be our speaker. So I've known David for quite a few years. He's a professor of mathematics at UWC. He's the Deputy Dean of Science at UWC as well for teaching and learning. He serves on a number of mathematics boards in South Africa. So the Council of the South African Mathematics Society. He serves on the board of the South African Mathematics Foundation. And he serves on the Council of the African Institute for Mathematical Sciences, AIMS, which I'm sure many of us are familiar with in the seminar. So before joining the University of the Western Cape, David held positions at the University of Cape Town, where he completed his PhD in 1995, and at the University of Stellenbosch, where I got to know him. And over the course of his academic career, he's been a research guest at over 20 universities across the globe and held visiting positions at the University of Bremen in Germany and the Brno University of Technology in the Czech Republic. David makes sure that mathematics does not take all his time away from his life's main passions, his family, and the Fynbos mountains and oceans of the Western Cape. But yeah, we really proud to have you here today, and we look forward to your talk, David.
Great, thanks, Bruce. Thanks everyone for joining. It's nice to be here. It's a really nice opportunity. Talk that I'm giving comes from research that I've been doing, and I should acknowledge some of the people who may be in this room. I'm not looking through all the participants lists at the moment, but certainly the people at UWC that work with me. Ando Razafindra-Koto. Ando has been influential in a lot of these thoughts. And then my students, in particular, Fikri Hans Asfor and Minani Iragi. Fikri Hans was at AIMS and came through to UWC, and Minani completed a couple of degrees at UWC and is now at UNISA. So they've all played a role in forming these ideas that I want to share with you today. I wanted to start off with a quote that I always find interesting, coming from William Thurston. I don't know if you know who Bill Thurston was, or if you know his name. When he was talking about, well, a number of things, but about how we communicate mathematics. And here he's saying, we're not trying to meet some abstract production quota of definitions, theorems, and proofs. I don't know if you sometimes feel that, that when you're doing your research, when you're producing a paper or whatever, it's not just because we're chasing a target. And sadly, that's often the case these days in terms of what the administration puts on us, but it's more than that. And he goes on to say, the measure of our success is whether what we do enables people to understand and think more clearly and effectively about mathematics. And I find that quite motivational, partly in the context, obviously, of giving a talk. You want to make sure that people understand. But in the mathematics that we do, you know, the purpose of it is to make sure that other people come with us. And the maths that we produce helps people to see things more clearly than they could beforehand. If you haven't ever seen the article, it's on proof and progress in mathematics. It's from quite a while back now, but it's an interesting read. You may want to go and have a look. I'm sure you'll find it online easily. He goes on in that to talk a little bit about how we communicate mathematics in colloquia. And this may also sound familiar. So mathematicians have developed a habits of communication that are often dysfunctional. Organizers of colloquium talks exhort speakers to explain things in elementary terms. So that's what Bruce said to me before I give this talk. Nonetheless, most of the audience at an average colloquium talk gets little value from it. Perhaps they are lost within the first 5 minutes and they sit silently through the remaining 55. I've got a bit less. Or perhaps they quickly lose interest. This was before the days of Zoom colloquia where they can do their email, because the speaker plunges into technical details without presenting any reason to investigate them. And then, I'm sure this is something we're familiar with, at the end of the talk, a few mathematicians who are close to the subject ask a question or two to avoid embarrassment. So I hope that's not going to be the case from this talk. But I think it is a challenge. to think about how we communicate our mathematics. So I'll bear that in mind as I go along. And now I've got to move my picture out the way because it's going to obscure. So I wanted to talk to you about some things that I do in category theory. And but I thought I would start in trying to motivate how a topologist views first-year calculus. I don't know how many of you out there have taught standard first-year calculus using perhaps one of the ubiquitous American-style textbooks. These are two theorems that we do with our first-year students usually at some point when we're wanting to do some applications. And probably, depending on the tradition, I'm guessing probably we wave our hands a bit about these theorems. We don't actually prove them to the first years. Maybe later on when you get to some real analysis course, you may actually go for a proof. So the first one, the extreme value theorem, which is one that I'm guessing we're familiar with. It says, you know, you start at a point A and you go to some point, say B, with your function. So you're working on that interval and you say to the students, well, if you're working on that closed interval, somewhere on that closed interval, your function will actually attain its maximum and its minimum, which in this case, it hits the minimum is actually at the end point and the maximum will be up here. How does a topologist see that? So what a topologist sees when you see that theorem is actually, if you take the image of this function, what you're getting is, so this, if you think of it on the y-axis, that's the image of the interval AB under the function. So if you take the, oops, my pen is misbehaving. We take the image of the closed interval AB. What do you get? Well, you get that this is also a closed and bounded interval. And closed and bounded in the language of topology applied to the real line is compact. So what this is really saying is that the image of AB is compact. In other words, if you take the image of this closed interval from A to B under the continuous map F, over here you get the F of AB, and that's also compact, which means it's closed and bounded. Bounded means that there's going to be a maximum and a minimum, and the closed bit means that it actually attains those maxima and minima because those endpoints are inside because the interval is closed. So topologist's version of the extreme value theorem is essentially that the continuous image of a compact space is compact. Now, we would never teach our first years the extreme value theorem in that language, but that's what it comes down to. As I say, if you take a topologist's view of the extreme value theorem. The other theorem that we particularly wave our hands about is the intermediate value theorem, which is very intuitive, but harder to prove, certainly at a first year level. And then you're saying that if you've got some value n, which lies in between the function value at the beginning of the interval and the function value at the end, then there is some place, at least one place C, where the function attains that value n. What is that in terms of the language of a topologist? Well, in the language of a topologist, you're saying that the image of a connected space is connected. And again, we wouldn't use this language probably if we were teaching it to our first year students, but that's the heart of what those two theorems are saying. So in my talk today, I want to talk a little bit about how I understand topology from a categorical point of view in particular, and then just come back to these theorems to see, well, how do you prove these theorems in the context of the type of mathematics that I'm doing? So my question is, to start with, what do you need to do topology? I'm wanting to think fairly abstractly and say, I'm happy to do topology in any context where I've got the basic tools that are required to do topology, as I'm calling it. Well, you need some notion of space, and my spaces are what I call objects in a category. So I've got a category, and the objects, the elements of that category are the spaces, and I've got what I would intuitively think of as continuous maps. Those are the arrows in the category, and the basic algebra that you've got to work with is you've got an associative composition and you've got identity maps. Now, I don't know if you are familiar with category theory or not. If you're familiar, then this is straightforward, but these are the basic building blocks that we use everywhere. You know, if we're doing algebra, vector spaces, whatever, we've got some notion of a mathematical object or a mathematical structure, and for that to be useful, we always consider what are the natural maps between these structures, be they linear maps, continuous maps, differentiable, homeomorphisms, homomorphisms. I think we're all familiar with this kind of language. So you may just want to think of your favorite category at the back of your mind if you want to get some sort of intuition. So that's the starting point. The next thing that you want is you want to be able to talk about subspaces. In doing topology, it's crucial that you have a notion of subspace. And for us, that's sufficient to think of that you've got a complete lattice. Think of the power set if you like, but it doesn't have to be the power set. It's so to every object, every space that you're considering, you've got a complete lattice. And that lattice is ordered. And because it's complete, it's got a smallest element and a largest element, which I'll call 0 and 1. Again, if you want to fall back on your intuition of sets and topological spaces, we're talking about the power set with the empty set and the whole set. And then crucially, certainly when I teach topology to students for the first time, within the first lecture, I spend a lot of time talking about image and pre-image. That comes up everywhere. Of course, in particular, when you talk about continuous maps, you've got to talk about the pre-image of an open set. But you can't do any topology without spending some time talking about image and pre-image. So we're going to ask that we've got this notion of image and pre-image available in our category. So that means that taking a map so you start off with such an F, and then you transfer it to an assignment between the sub objects. So you take an image and you take a pre-image, and that's somehow induced by the map F that you've got at your disposal. So as I've said, along your guiding intuition could be just simply taking topological spaces and continuous maps, but bear in mind we wanted to lift this to a level of abstraction that will hopefully set us free to be able to prove more concisely and more powerfully some of the theorems that we know and love in topology. All right, so those are the basic things that we want. It's probably worth spending a little bit of time just quickly going over Galois connections or adjunctions, depending on the vocabulary that you use. You may or may not be familiar with this notion. So an adjunction relationship or a Galois connection in the context of two here, we've got to remember the px and py are complete lattices, and you've got these maps going backwards and forwards between them. So this backwards and forwards has a particularly tight link. And when you first think of image and pre-image, you may or may not think of it quite in terms of this tight link, but the link is that the image of M is below N if and only if M is below the pre-image of N. Of course, if you're just working at the level of sets, you may think in terms of points, but you might be used to thinking of, so f of A is contained in B is the same as saying that A is contained in the preimage of B. I don't know how you're used to thinking of image and preimage and how they relate to each other, but they have this tight relationship. And any order preserving maps between lattices that have this kind of interrelation, we call an adjunction or a Galois connection. And there are a number of things that follow straight away if you've got that. Probably most importantly is that the image, so as you go from left to right, the image preserves joins or suprema. And conversely, because there's this duality really between the two, conversely, the preimage is going to preserve infima. In particular, the preimage will preserve the infima of the empty set, which is the top element of the lattice, and the image will preserve the infima, and the supremum of the empty set, which is the bottom element. But that's one thing. The other thing which you often need to fall back on, especially if you're doing set theoretic topology, is some of these observations here, which I've written in lattice theoretic notation, not with a meet and a join and a less than, not intersections, but you can think of intersection and set containment. So the image can just be given as you take the image as the meet of all those subsets, if you like to think in terms of subsets of Y, which are below the preimage. So you can use, in other words, you can use preimage to define image. And conversely, you can use image to define preimage. That's no surprise really, but that follows just from general nonsense, thinking about Galois connections and this tight relationship that you have. Other things which you often need is, M is below the preimage of the image, and conversely, the image of the preimage is below N. And if you do these 3 times, backwards, forwards, backwards, you get back to where you started. These are general facts which are very useful to have at our disposal. So in the categorical case, when you're thinking in the category, you think of preimage as pullback. So what does that mean? Something is a pullback square. So here's your map F. You've got this sub-object, which is thought of as an arrow. And what a pullback does is it's optimal. If I had another way of entering with maps N and X, then this way will factor through the pullback. So it's an optimal way of completing that square. So pre-image categorically, you just think of as pullback. And image, if we've got image at our disposal through this adjunction that we talked about, that produces a factorization of any map. So typically you might want to think of this as a surjection if you're building a set theoretic kind of intuition. That's just the image. So you've got a function from X to Y. Then of course you can take f of X, which is a subset of Y, and the map F factors through its image. And these maps, these surjections are going to be important for us. So we give them the name E, and we'll refer to those over and over. So pre-image is pullback, image allows us to factorize. There are some cases, and it's particularly the case in sets, that the pre-image map, remember, because it was a left adjoint, because of this Galois connection, it preserved meet. But in fact, it sometimes also preserves join, suprema. Not always, but in many cases it does. So that's certainly the case in sets. If that's the case, then because it preserves suprema as well, you get an adjunction on the other side, which we call the dual image. So it's not in this picture, but you've also got the image, which runs in the same direction as dual image. But the image is not the same as F star. F star is defined, but now using the join instead of the meet. And this dual image, I'll give an example now that may help you to understand it. So if we fall back to the category of topological spaces, which is certainly my intuition, you've got this lattice, which is the Boolean algebra of all the subspaces or subsets of the topological space X. Image and preimage, what we're used to. And then preimage preserves not only intersection, but it also preserves union. And if you just think of a simple little map, say mapping from X to X squared, then so what's the image of this set? Well, you square everything inside here. That really gives you all real numbers between 0 and 4. If you take the preimage, that's all real numbers whose square is in that interval between -1 and 2. So you get all real numbers between -√2 and √2. Whereas if you take the dual image, you get from -infinity up to 4, as against from 0 up to 4. So that's really the difference between, let's go back to the previous. So remember, the dual image in the language of sets will be the union of all those subsets whose preimage is below what you're taking the dual image of. And the preimage of negative numbers is actually empty. There's nothing that gets mapped to the negative numbers. So you can add them all in and they get caught still in the dual image. So that might give you some feeling for the difference between these two. If you're working in the category of groups, with group homomorphisms, same concept, the lattice of subgroups, which is different to the lattice of subsets. But still you have meters intersection, but join is more complex. You have to take the subgroup generated by union. Image and preimage, those are the same. But here, preimage doesn't preserve unions. In general, the preimage of the single element group, the smallest subgroup, which is not empty, it's got one element, that's not necessarily the single element group, only if F is injective. So you have to be careful. You don't always have these things at your disposal. Another category that people may or may not be familiar with, graphs. So think of graphs, directed graphs. You've got the vertices and the edges, and the maps that we consider are those that preserve the edges. Very similar kind of situation. They would also fall into this broader picture that we're painting. Right, so that's to give you some background as to the categorical field that we want to play in, if you like. And then the question is, well, what can we do if we've got this? So historically, going back to the late 1980s, the idea was to do topology in a category using the notion of closure. There are different ways that you can describe the topological space, but in this context, closure is a very nice, succinct way to transfer topological ideas to this categorical setting. So what's a closure operator? It takes the subspaces of X to subspaces of X, if you like. The closure is bigger than M. This closure operation preserves order. And you're asking that because you're wanting to do topological things, you want your arrows in the category to be continuous, which means the image of the closure is below the closure of the image. That's just one standard way to describe continuity. Another way may be to think of, well, why don't you take interiors? And there was quite a long break before people looked at interior operators, partly because you may think, well, surely there's just an obvious duality. We know from topology you can use closure or interior, you get the same thing. But because you don't necessarily have a Boolean algebra when you're taking this lattice, the notion of interior and closure are different in general in this categorical setting. So you can reasonably consider interior operators as well. So similar to closure operators, but the interior is smaller than M. There's also preserve order, and your maps are continuous. The preimage of the interior is below the interior of the preimage every time. Okay, I'm not going to spend any time talking about those. That's really just the historical background. What we've spent some time working with is the idea of a topogenous order, which also dates back to a long time in topology, where the first person really to look at them was Ákos Sászár from Hungary. But he thought of them more in terms of uniform spaces and thinking of families of such orders. So if you take a single order, it's like thinking about a topology. What do we ask for a topogenous order? So a topogenous order is, again, there's one for every object in the category. And these are relations with these simple properties. So if M is below N, then it means that M is less than or equal to N. And then you've got a degree of transitivity. If M is less than or equal to N, and N is topogenously below P, and P is less than or equal to Q, then in fact M is topogenously below Q. And then you ask again for continuity. So, and the easiest way to describe that is if you've got two, one is below the other, then that relation is preserved by the preimage. So we'll think of all of these orders on our category, and we'll order them as a collection themselves, just using the obvious, one order relation is below another if it's contained in the other order relation. So what's the point of thinking about these things? Maybe it gives you some feeling if you just think of an example. So for a subset of a topological space to be below another subset, that's one possibility as a definition, is for M to be contained in the interior of N. Then we say that M is below. If we're working in groups, you could say that the group G is below the group H, just means that there's a normal subgroup somewhere in between the subgroup G and the subgroup H. So those are just examples of such a topogenous order. And there are many, and these kinds of orders have been studied from various angles in order theory for sure. So for graphs, you could just say that the one subgraph is below another as long as the edges are well and truly contained in it. For instance, that's another way. And you could probably easily think of other definitions that would satisfy those three axioms. All right, so topogenous orders actually subsume interior and closure operators. So that's the one reason why we found them interesting to study, because the theory of closure operators, the theory of interior operators are really just occurring within a theory of topogenous orders. And the order relations which preserve suprema or respect suprema. So in other words, if you've got a hollow of Mi or below N, then the supremum, my face is in the way, then the supremum is also below N. That's if it's preserved, if it respects suprema. And similarly for infima, if M is below a hollow of Ni, then M is below the meet. That doesn't necessarily have to happen, as you know, with suprema and infima, but these ones, which we'll call the join and meet topogenous orders, are the ones that actually correspond nicely to interior and closure operators. So the ones that respect join are exactly the same as the interior operators. Maybe it's not worth spending time on the proof, but the concept is fairly straightforward. So you want to define the interior, you just take the join of everything which is below M. Now remember in the example that we had for topological spaces where below meant contained in the interior, or that you can see came from exactly the inverse idea that you get such a topogenous order by saying M is below N if M is less than the interior. So this way you can move backwards and forwards and in fact show that the collection of join respecting or supremum respecting topogenous orders is exactly the interior operators. So that's what interior operators are, and closure operators are conversely exactly the ones that respect infima, that respect meet. And these occur then within the theory of topogenous orders. That little picture there may or may not be suggestive depending on how you think. So obviously for any meet preserving or join preserving topogenous order is occurring as a topogenous order, the point is that because of the nice behavior, we can always find a natural way to take a topogenous order to one that is the closest join preserving or the closest meet preserving to it. So you get a nice tight connection with closure and interior living inside the world of topogenous orders. So the comment there is really just to say, you've got to be careful. There's not a duality, as I said earlier, between interior and closure, but there is an element of symmetry, if you want to call it that. But also you can see that many theorems that you might prove are really just expressions of the same theorem that you can prove in the world of topogenous orders. So that's one reason why we like to think of them in this way. Okay. My talk was about an ordered view of continuous maps. So I wanted to really just spend the rest of the time thinking about continuous maps and how we can understand them. And I guess maybe not the point, but one of the feelings I want to give across in my talk is, how does one deal with abstraction? What motivates you to abstraction? And then once you've taken an idea to a more abstract level, is it useful? What does it prove? What does it help you with? So once we've got this idea that to do topology, as long as we've got this basic set of structures, of sub-objects and the like, nice maps, we then impose this idea of order on our category. And then one of the first things we asked is this first point, that this order, the maps should be continuous. And then it's very easy to prove that these other three conditions are equivalent to continuity. So you can say it this way. You can say if the image is below n, then m is below the preimage. And then you can use dual image there's an obvious similarity here in what you're writing down using dual image. And then this last one might look a little bit different, but it's how image and dual image together can help to describe continuity. So there's a fairly straightforward to prove. I think I wrote down just the proof of why 1 and 2 are the same, just to give you a feeling for, are the proofs easy? And that's one reason why we go for abstraction, is if we hit the right level of abstraction, our proofs should become clearer, easier. So if we're wanting to prove that 1 implies 2, so let's start with f of m below n. Then remember just the general fact that we had from a Galois correspondence was that it's always true that m is less than or equal to the preimage of the image. Then because of property 1, we apply preimage to both sides of this, and we get that the preimage of fm is below preimage of m. Then because of the second property of the topogenous order, that means that this is transitive across there, so m is below preimage of n. And that gives us what we wanted to show. So it's very straightforward just to argue through. And if you go the other way around, now you're using again the property of a Galois connection, that the image of the preimage is below m. Then again, you then take the transitivity, and you have, if m is below n, then that means that this one, image of the preimage is below n, and then you apply 2, and you get condition 1 falling out. So it's a very straightforward proof, and you can do the others, similar games really, just using properties of Galois correspondences and the key properties that you've got for your topogenous order. Now you can look at all of these and think about them and what they might mean. I wanted to zoom in particularly on this second condition, which is quite suggestive, because we spoke about Galois connections earlier, and what was special about a Galois connection was that you had an if and only if, and then of course we had this relation. We had the relation on the P of X that we were looking at. So this condition 2 is sort of half of what one might ask for a Galois connection when you've got this other order relation now in play. So a very natural question is, well, what are the maps where you do in fact get that, sorry, this, what are the maps where you do in fact get a double-headed arrow there? That must be some nice collection of maps, surely, to have that nice symmetry. And so proceeding in that way, we can define a whole bunch of different special maps. And we give them names, which obviously are names because they have some connection in certain instances with existing notions. So we basically take the previous, let me go back again. We take these previous and we ask each time that the arrow just be a double arrow. So this one was interesting because it looked like Galois correspondence, but in fact, all of them are probably interesting if we reverse the arrow. And those are the definitions that we get. So we say it's final if we've got a double-headed arrow for that notion of continuity. We say it's strict if we have a sort of like this Galois connection kind of property. Co-strict is again the same, but now we're using the dual image instead of the image. And then initial is the one which links image and dual image together in a way similar to property 1. So that's easy to do. You simply make new definitions. But remember what I said at the beginning when I was talking about the quote from BillThurston's work is we don't just spit out our definitions and prove things. Hopefully it's because it makes things clearer or helps us to see things differently. So in the world of topological spaces, this is the one relation that I've spoken about already, if M is below N, if M is in the interior. But you could equally have this notion that M is below N if the closure of M is smaller than N. And these are different relations. There's definitely going to be some interplay between them, but they're different relations. And to be strict for this relation is the same as to be co-strict for that relation. And that's the same as being an open map. And if you switch it over, to be strict for this relation is to be a closed map. If you take initial, then that's what is already considered an initial map. Maybe you think of it as having the weak topology. And that's another name used for initial map. And a final map is slightly more strong, as to be an hereditary quotient. So these are very natural, as I said. They're suggested from the abstract work, but one would expect them to be things that are studied already because they are very natural. And that's what they turn out to be in the world of topology. When you come to groups, remember those numbers 3 and 4 won't be at our disposal because we don't have dual image. So strict really just comes out to being preserving normal subgroups. And final is just the same as being surjective. And that's, I don't know if typical is too strong a word, but generally the more algebraic settings, these topological notions maybe aren't quite as rich as they would be in the topological settings, and that's not surprising. So in groups, the definitions that come out are not as nuanced as they might be in topology. So one thing that you ask yourself if you've got a collection of maps is, what sort of properties does this class of maps have? So now I've got 4 classes of maps, and I would like to say, can I make any general statements about these classes? And one thing that's particularly useful, given the types of constructions that we do, if a class of maps is stably closed, and you say that f is stably in, the little f is stably in the class big F, means that, so if you take an f here, which is in some class of maps, and you then take a pullback of that, and you get another one here, and you ask, will that also be in F? So if F is in F, does it necessarily follow that when you take a pullback, it's also there? So then you say that this little f is stably in the class of maps F. And if that happens particularly for these morphisms E, which are the surjections intuitively, then that's often a very useful property. And then we say that images are pullback stable if we have that property. Another property that we ask for a class of maps is, if we've got two maps and we compose them, do they stay in the class? That's a very natural, it's almost like an ideal kind of question. So F might be closed under composition. The other property that is very useful to consider is some sort of cancellation. So we would say that it's right cancelable if when you've got this composition is in F, then you can, sorry, that's left cancelable. You can scratch out on the left and you get the G's in F, and conversely to be right cancelable. That's another set of properties that is handy. And these classes of maps, these four that we just abstractly defined, they all contain the isomorphisms. So the isomorphisms have these properties, and they're all closed under composition. The initial maps are left cancelable, the final maps are right cancelable, and the other classes of maps, so strict, co-strict, and final, are left cancelable only for sub-object maps. Those are injections, if you like, injective maps intuitively. And they are right cancelable, the initial strict and co-strict, with respect to surjections, this class E that we've got. So that's fairly nice. Those are the sorts of properties that you hope to be able to prove about a collection of maps that you're considering. So now we're in a place to be able to come back to where I started. Remember the topologist's view of the mean value theorem and the intermediate value theorem. And to start with, we just want to introduce this notion of a terminal object in a category, which is probably something that's fairly familiar. It's a special object where for any other object in the category, there's precisely one arrow that ends in it. Typically, this would be the 1-point space if you're working in topology. If you're working in groups, it's the trivial group with just one element in it. It can be different in different categories, but in many of the categories that you're familiar with, it's probably a single element set with the appropriate structure on it. So that's the idea of a terminal object. And then another one that I want to introduce is what is sort of akin to a 2-point discrete space in topology. Co-products are just disjoint sums, if you like, in the categorical language. So if you've got two, let's just think topologically, we've got 2 points, 2 terminal objects, and we combine them into one space, you'll get a two element set, and it's going to have the discrete topology. Both points will be open. In the category of groups, this has become something quite different. It's not just a 2-element group. So you have to be careful what it might mean, but categorically, it's a very simple thing to describe. Why are we doing this? Well, that lets us talk about the notion of constant map. And I think this is very easy to agree is a natural notion of constant map. Remember, in our category, we can factor maps. So we start with F and we factor it. And when we factor it, it goes through a single point intuitively. Then, of course, the map is constant. So that's our definition of constant in this abstract setting, that when we factor it, it goes through a terminal object. And then we come to very simple definitions that, depending on what background you have in topology, you may say, oh, that makes sense, or you may think, where on earth did he get that idea from? So the first is, what do we mean by compactness? So maybe just pause and step back again. We've got a category. We had the machinery we required to be able to talk of subspaces, image, pre-image. We then said, let's consider some abstract relation on our category, this topogenous order. And now once we've got that, we say, relative to this relation, we're going to describe or call an object compact if this terminal map is a stably strict map. In other words, any pullback of that terminal map is also strict. So remember F, the class of all strict maps, we pull it back. Now you can do a similar definition for the other classes of maps. We haven't tried that. You can do all sorts of things. I'm just concentrating on this one particular case. Connected, somewhat different. Connected is not talking about these different classes of maps. It's coming back to the picture that's on the screen and saying that your space is connected if when you take a map to a 2-point discrete space, thinking topologically, it's going to have to be constant. You can't split it into two different parts. That's what connectedness is about. So those are very easy definitions to give in this context. If you want to be convinced that these really extend what happens in topology, that's of course another question. I think number 2 is probably easier to be convinced. Number 1, you may need to go back to some of your topological theorems to see why does that necessarily describe compactness. The point is that it does. If you take as your relations this topogenous order, M is below N, if the M is in the closure of M is inside N, then you get exactly compactness in the usual sense, falling out of that definition. But of course, we have many compactness notions because we have many possible topogenous orders. So how do I prove the mean value theorem now that I've got this machinery behind me? So the mean value theorem, remember, was that the image of a compact space is compact. So we start with a topogenous order. We do ask that our images are pullback stable, and then we end up being able to say that the image of a compact space is compact. So we can prove the mean value theorem. How do we prove that? And it's an easy proof. As I've said a few times, one of the values of abstraction should be that your proofs become simpler and more powerful, more transportable. So let's see, we've got that X is compact, and we take an image here. So this here is a map in this class E, and we're wanting to see whether Y is compact. So we're wanting to ask whether is this thing stably strict. That's the question. Then we've shown that Y is also compact. Now, so we take the map to the terminal object. Because there's exactly one map to the terminal object from anything, there's this composition. Here is also the unique map from X to terminal object. Now, X was compact, so that means that this must be strict if we take pullbacks in both those squares. So I take the pullback of ty, get t tilde, and then I take the pullback of e to get e tilde, and that means that each of these squares are pullbacks. I'm going to denote it like this, and that means the bigger square is a pullback. So as a pullback of this terminal map from X, this one is strict. So that's strict. This is also an E because we asked that images are pullback stable. And that means we can cancel it on the right. And that means that T tilde Y is strict, which means that TY is stably strict because this pullback is also strict. So that's our proof that the image of a compact space is compact in the context of topogenous orders. What about the intermediate value theorem? So the intermediate value theorem is that the image of a connected space is connected. That's probably an easier proof, really. So what are we doing now? We've got that X is connected, and we want to show that Y is connected. So the question is this map here constant or not? That's what we want to ask. So we take any map from Y to the two-point space, if you like. Then we compose it with this image map over here. And then because X is connected, this must be constant. So when we factorize it, it factors through 1 because it is constant. But there's a unique map from Y to that, which we call TY. And because these are both in E, it forces this one to also be in E. And as a result, that means that what we've got here is the factorization of F, but it goes through the terminal object. So F must be constant. So Y is also connected. So I hope I've given you some sort of idea as to, I suppose you may see it as the game that we play, but also why the level of abstraction really does allow you to still prove theorems that are of fundamental importance. And it's, I suppose, for you to judge whether you think this makes them easier or not. And I think in general, just to finish off with a quote as I started, any good theorem should have several proofs. This is a quote by Michael Atiyah, which could be used in a number of contexts, really. The more proofs, the better. And there are two reasons for that. Usually different proofs have different strengths and weaknesses. So you can learn things differently because of the strengths and weaknesses of the proofs. But they shouldn't just be repetitions of each other. If the proof is useful, they should give you generalizations in different ways, and they should help you to take that result and use it further in other contexts. And that's really, I suppose, what I wanted to demonstrate in what I was talking about. So thanks very much. Those are just some of the references that are relevant to the talk. And I don't know if there are any questions, but I think I've managed to not use my full 3 hours, so there may be a bit of time for that as well. Thank you.